In this problem, you're going to be determining the electron configuration, spectroscopic notation, noble gas configuration, and the orbital filling of the element xenon, which is notated Xe. Now, the first thing we're going to do is we're going to take a look at the reference tables, which will tell you, if you're on your periodic table, that the electron configuration, the major energy level notation, is 2-8-18-18-8 for xenon. And again, you can find that on the bottom left-hand corner of the element symbol on your periodic table. That just means that there are 2 electrons in the first energy level, 8 in the second, 18 in the third, 18 in the fourth, and in the fifth there are 8 valence electrons, a full valence shell. Then we're going to write the spectroscopic notation. Now, the only difference between the spectroscopic notation and the electron configuration notation is that we're subdividing these major energy levels into sublevels now. So we'll start from the bottom of this diagram, and you can use the diagram on the right, which goes from lowest energy on the bottom to highest energy on the top. And we start at the lowest energy, which is 1s. So 1s, and every orbital holds 2 electrons. There's only one box that's going to be 1s2. We then hop to the next energy level, which has a total of 8 electrons. 2 of them are going to be in the 2s orbital. 6 of them are going to be in the 2p orbital. You can see that just by looking at the diagram right there. We'll continue to the third energy level now, and we continue with 3s2, 3p6. Okay, and that's the next highest. And then you go to the fourth energy level, 4s2, then something interesting happens. You actually go back to the 3d sublevel. The reason that's possible is because there's just more space available for that 3d. So 4s2, then 3d10. We're going to continue down on the bottom here to make a little bit more space. The next is 4p, and that's completely full, 4p6. We then hop to the fifth energy level for 5s2, and then back down again to the 4d sublevel, 4d10, and finally 5p6. And if you add the total number of electrons up, you're going to see a total of 54, and you should see that for both of them. So 2 plus 8 plus 18 plus 18 plus 8 is going to be 54. 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 10 plus 6 is also going to be 54, and that's how you can double check yourself there. Now, there's one more notation that we can use called the noble gas configuration, and we just look on the periodic table for the noble gas on the second highest energy level here, which is the fourth energy level. That's going to be krypton. So we go ahead and we write Kr in a box. And then we literally just take everything on the 5th and the 4d sublevel beyond that, and we write that out again. So 5s2, 4d10, and 5p6. And this works because that Kr is going to be the same electron configuration as everything up to the 5s2 orbital. So all that stuff right here is going to be notated right here as well. It's important to keep in mind that we only use the noble gases, meaning group 18, for that annotation there. So you can't use, for example, chlorine. You can't start with chlorine. You have to start with either krypton or helium or any of those noble gases. So let's finish this off by going ahead and filling in the orbital diagram. I'm just going to zoom in here so you can see a nice clear picture. And I'll just zoom this down a little also so that you can see the noble gas configuration. That'll help us out. And we're just going to fill these using a set of rules. So firstly, Alfbau's rule says that we start from the bottom, which is going to be the lowest energy orbital, which is the 1s. And that's going to be completely full. So we'll fill it with one up arrow and one down arrow, because according to Pauli exclusion's principle, we can't have 2 electrons that are in the same quantum state, so we give them opposite spins. We then go to the next energy level, the 2s, and we fill that with 2 electrons, one up, one down spin. And then we go to the 2p orbital, and we have to follow Hund's rule here. There are 6 electrons, but we have to fill all of those orbitals with at least 1 electron before we go back and fill them again. So 2p up for the px, we call it. The py is going to have one up. The pz is going to have one up. We're going to go back and downspin for the px, downspin for the py, downspin for the pz. We then go to the third energy level, and that's completely full, so we'll fill those up. 3s is going to fill up first, and then 3p up, 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 and down, down, down. Okay. Then to the 4s, up, down. And then we go to the 3d, because there's going to be more space available now, and so it just turns out that we're in the third energy level. And again, we're going to do the same thing as we did for the p's. Up arrows on all of them, down arrows on all of them, again because of the Hans rule there. And then 4p is going to be completely full, so let's fill that up first, and then down, down, down. And then we get to the valence level. So the 5s, completely full. Again, down to the 4d, because just energy-wise, that's the way it works. All up arrows, and then all down arrows. And finally, the 5p. And we, again, fill up, 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 and down, down, down. And that's going to give us our full orbital diagram filled with all of the electrons and all their correct spin states.